I will make you host, Simba.
Thanks. Great. I have my wrong window open. Let me move that. Cool. Hey everyone, excited to be doing a webinar today. We haven't done one in a little while. Today we're going to be talking about a variety of different things. The main focus is really going to dive into how feature stores work, why they were designed the way they are, and yeah, generally like how they work. Um, so when we first learned machine learning, at least when I did, I was kind of taught that we have these models, we have these nice CSVs, and we spend all of our time iterating on models such that we can kind of achieve the highest results. So a lot of the focus is on models, hyperparameter tuning, etc. Um, However, I'm here to tell you that those perfect CSVs do not exist. Unfortunately, in reality, as most of us know, most of our time is actually spent on the data itself, on building better features so that we can actually build models that are performant. So I'm sorry to say, but entering kind of lied to you. Not really, but the way the course in the way most people learn ML is very structured around the model bit because that's a bit that's different. It's a lot of focus has obviously gone into there's a lot of breakthroughs that have happened, especially as of recent. But realities, as usual, is typically very different. It's just very messy. It's very ad hoc, and a lot of time is being spent fully focused on coming up and iterating. And that process of how do we take dirty data, make it clean, turn it into features, continuously iterate on those, work as a team. Um, we don't really learn that. And honestly, most companies are kind of winging it. So there's this sort of ad hoc nature to the ML process. So today, we're going to talk a bit about that problem, the data problem in machine learning. We'll talk about feature stores, how they work, how they look, etc. And then we'll actually dive deeper into the feature store internals. So what do feature stores do? They do five things, generally. They facilitate deployment. And what I mean is they make it easier to deploy your features. They enhance collaboration, organize experimentation, increase reliability, and preserve compliance. Um, so here's how we build a traditional feature. We work in notebooks, we interact with our data infrastructure, and typically we start with this experimentation paradigm. So experimentation, oftentimes we're going to be working with things like pandas, DuckDB, etc. We're working in a notebook. The data set is typically a sample or at least a static form of the data. And then, yeah, most of our time is spent in this experimentation phase. And then we need to go productionize it. When we productionize it, um, things change. So all of a sudden we have to worry about data that's changing. We have to worry about streaming features. We have to worry about batch features. We have to worry about like on-demand features. We have to worry about latency, throughput, freshness, all these concepts that happen in production, monitoring, what happens when the streaming pipeline fails. What happens if there's new data that comes in that just doesn't mesh well? What happens if our features move? So there's all these problems that happen in production that we don't have to worry about in experimentation. It gets even worse when you deal with streaming because now you have to start worrying about backfilling, back pressure, and much more. So there's this like chasm between our notebook environment and production. Like getting those notebook features into production is really hard. Part of why feature stores and Featureform specifically exists is to bridge that chasm so that it becomes much easier to take those Jupyter features and put them in production. This is maybe another way to visualize You can really quickly build really awesome models and features in notebook settings. It's what we're typically trained to do. It's what we're very good at. When we start worrying about production, it just gets much messier. The way I've seen it solved is two ways. Either data scientists deploy their own, or ML passes to like another team, like an ML eng team or a data eng team. And the data eng, ML eng side, it requires like two separate sets of teams. You're passing around notebooks. There's a lot of communication and organization and a lot that has to happen. And generally it's slower, less efficient, and no one's really happy because both, like data scientists are reliant on another team to productionize things. Sometimes they won't be able to. And then for the data eng team or whoever, it can be a very long list of things to put in production, and it can get very painful. The other thing that I've seen is data scientists deploying their own. This also, in my opinion, this is actually the way to go, that it should be democratized to data scientists. However, with most current tool sets, when we start worrying again about things like how do we build a production grade incremental processing pipeline, it just becomes out of scope. It's just hard to do, and it's really hard to do right. And if you have a model in production, like a recommendation system, when it goes wrong, bad things happen. So, yeah, in both situations today, it can be very painful. And so parts of what feature stores do is facilitate deployment. And so we'll get into that soon. The other thing that they do is they enhance collaboration, organize experimentation. A way to visualize this is if I were to ask you, for all the features you have in production today, where's the documentation and what state is it in? What would your answer be? Maybe you would have to dig through some untitled notebooks. You'd have to look at feature table V7. You'd have to deal with all of this, I guess, mess that was created. That all kind of comes together in this duct tape fashion to build your production feature. That's kind of the reality today. And a lot of what feature stores do and what Featureform aims to do is make it so that this whole process becomes much more streamlined. The name Featureform, what I wanted was Terraform for features. So the goal here is to make it so that we have this declarative API, kind of like Terraform, that makes it much easier to iterate on things. You won't have all these ad hoc scripts you have to run at specific times. Everything is versioned, everything is documented, and it's all in kind of one searchable index place. Finally, there's monitoring and reliability. Once the feature's in production, it's now a production artifact. Like exists as long as the model using it or continues to use it, it exists. And so it's not really a good idea to push new features into production without understanding how they're changing, what they're doing, different distributions maybe that you're serving. And so without proper drift monitoring, this can get really bad very quickly. And then finally, preserving compliance. With a lot of the models, especially depending on what company you're in, preserving compliance becomes really crucial. It kind of, it's a must-have for some companies. For some companies, it doesn't matter. Like if you're working on certain data sets, it doesn't matter. For others, it's extremely important. And a good feature store like Featureform should kind of mesh in compliance and governance directly into the APIs so that it feels very natural and it makes it impossible to accidentally use data where it shouldn't be used. So those are the problems. Now, how do feature stores solve this? So at first, it seems like it's not really the same, right? Because when you think of the term feature store, you think of like a database where features are stored. It's kind of what the name implies, right? But is that really solving like deployment? Like if all my problems are on the transformation data pipelines, having some sync to store them and actually doesn't really solve any of my problems. When I think about collaboration and organization, a lot of the collaboration needs to happen on the building of the model. So it needs to happen on the data pipelines themselves, not on just like the final artifact, the final table. So there's kind of it's kind of a misnomer, at least not for everyone, but for a lot of companies, or a lot of feature stores, they kind of ignore these first two steps. They leave it to the user to build their transformations, productionize them, etc. And what they handle is the inference store and the training store. So these two places where you can store your features for use. Inference store is used for production, like it's like almost like a cache of the most recent features, and then the training store has the historical feature values for training. And then all of this runs on infrastructure today. So there's one flavor of feature store, which I will call the literal feature store. With the literal feature store, they literally store features. So if you look at Databricks' feature store Feast, what you'll find is a product that you write your feature tables into, and then it will allow you to serve them for both training and inference. But again, going back, all of the everything that has to do with productionizing the data pipelines is pushed to the user. So none of that kind of gets done. So there's this idea of like a physical feature store. Sometimes people call it a feature platform, which I think is a much more correct step in the right approach, where the transformations, the features are defined as code. So rather than the feature being defined as a table, it's defined as a code such that you can specify, hey, my feature is these 5 SQL transformations. It's this DAG. When you define it that way, the physical features or the feature platform will actually run those features. It will keep them up to date. It will allow you to serve them for both inference and production. The problem is that it will do this typically with a custom DSL and typically with custom infrastructure. So most physical feature stores, in fact, I believe every physical feature store on the market has its own compute engine that it wants you to use. And so if you're using Spark today or Snowflake or whatever, you would not be able to continue using Snowflake and do this. You would have something that sits next to it specifically for ML. And that kind of brought up the idea of a virtual feature store. With the virtual feature store, the concept is what would happen if rather than take the feature platform idea, the paradigm of you define your features as code, you run them, but you allow the users to kind of, with a plugin architecture, include their own compute and their own storage layers. And then you kind of layer the rest of the feature platform on top. And so how it ends up looking is that data scientists define their features as code in SQL, Python, PySpark, whatever. Featureform, or the virtual feature store, will take these definitions and it will store them, it will version them, it will document them, it will kind of give you all that. And also, it will orchestrate them on top of Spark, Redis, whatever, like whatever infrastructure you use to build and maintain those features, similar to a feature platform. So what's the difference between doing that and actually running those things yourself? Well, one is when you start dealing with stream processing, incremental processing, monitoring data pipelines, having data pipelines work at really high scale in a way that data scientists can write them themselves. So democratizing, building production grade pipelines to data scientists. That all gets done by the orchestrator. And then on top of that, you get monitoring, governance, collaboration, search and discovery, versioning, lineage, etc. So how are we able to pull this off? Like with the feature platforms, the way they do it is they came with their own processing engine. So they kind of own the entire transformation and storage stack in that way. And they also, I would say, have their own DSL. So in that way, if you combine those three things together, you end up with enough control that you can kind of make the user do what you need them to do to achieve high throughput and fast latency. Now, Featureform, we don't really have that luxury because we're letting you, the user, bring your own infrastructure. And on top of that, we need to be able to handle a lot of different permutations of infrastructure. For example, we have companies that use Spark and Snowflake together. We have companies that have Dynamo and Redis in production. And we have people who read from Spark data sources in Snowflake and vice versa, and kind of everything everywhere. So it was a very hard problem. Like, how can we do this? And not only do it, because there's ways you can just kind of make it work, but like mediocrely, where it won't really scale to like huge data sets. But how are we able to make this work at scale? So the answer is, firstly, that we let Featureform run in this kind of Kubernetes architecture. It's running there. When you're interacting with it, what it's doing is, for all the versioning, the latency, or sorry, the versioning, the lineage, the orchestrator, all that is living in a highly available service in Kubernetes. So that's step one. That's almost like the easy part. Okay, cool. We have this thing, it runs, it can scale. There's a lot of glue code. For example, we oftentimes have these jobs that we have to run, like to copy from Snowflake to Redis. There is no native Snowflake to Redis connector. So we actually have to run jobs in Kubernetes that actually will do that copy for you. So that's like the first step. It's just like make sure that we are Kubernetes native. This allows us to be run on-prem, hybrid, AWS, etc. So that's the first solution. It's like let Featureform run everywhere and let it scale anywhere. And that's what I was talking about. Like that glue comes in from the job pods. The more interesting thing that we've done is we actually, in the last year, have rewritten Featureform entirely around the idea of a lakehouse architecture. So what is this exactly? When you think of lakehouse architectures, typically one of the main things you should think about is a table format. So like Apache Iceberg, Delta, Hoodie, there are others, but those are like the three ones that the main ones. Featureform has mostly centralized around Iceberg, but we do also support Delta and Hoodie. And our view is that Iceberg is kind of becoming a standard and a de facto, and that the other table formats will all be interchangeable with Iceberg soon enough. So what is Iceberg? So originally how Featureform worked, let's take a step back, is we would write data into Parquet files. When an update would happen, we would go and add new Parquet files. We'd put them in slightly different directories. We'd have different ways to split them up. But in general, we just have this kind of giant bunch of Parquet files that we're just constantly writing to. This happened also streaming. As we maintain historical data, we just kind of pipe it into Parquet files. Now, the problem is that when Spark would do a query, like a join, it would still be quite slow because it would have to read all of the data. It would have to sort them. It'd have to kind of co-locate the things that they're joining into the same node. And it would be quite slow. We'd have to deal with, there's all these situations we'd have to deal with. Other things that would happen is sometimes we'd end up with files, those Parquet files of like that are very small. And it can add a ton of performance hits. So there's just a lot of situations we ran into where just our really simple, just like append Parquet files doesn't work. What Iceberg gave us, and then Delta, etc., what they provide, I think of it like an index. It's providing these metadata files, and it's specifying where different, for example, if you're doing data based on date, like you have time series data, you can make it such that Iceberg will keep track of where different blocks of dates are. And that's nice and all, but where it really becomes powerful is when you realize that all the query engines, like Spark, like Trino, like whatever, they're all able to use that metadata. And if you run a query, even DuckDB does this actually. When you run a query, it will use that metadata file to grab just the minimal number of data files it needs to grab. In fact, sometimes it will even just grab portions of data files, not even the whole file, so that it can really minimize the data it actually has to process and read. And for things like joins, it can be extremely fast in the same way. So you start to kind of add this almost database-like thinking to it, where you need to start thinking about your primary keys, your foreign keys, etc. So more of a relational style. It's not relational, but it does kind of move a step in that direction where I can start creating indices and control those indices. So that allowed us to go from where we were at, which was relatively naive. You just had to have a Spark cluster that was big enough to query your whole data set pretty much every time. And if you had multiple joins, you just had to have a really massive Spark cluster. With Iceberg, we've seen situations where those joins can drop by 90+% in time. Like the performance gains we've gotten from Iceberg are crazy. The other thing it's allowed us to do, so actually before I get into that, the other thing that we've also found, which has been really good for us, is here when you talk about the Lakehouse architecture, we saw Dremio, we saw Flink, we saw Spark. That all kind of makes sense. It's kind of like the usual suspects to an extent that you would expect to be able to process like S3 data or wherever, like Azure File Store. It doesn't really matter where you store it, but just like in a object store. As of the last few months, Snowflake has released the ability to also read and write Iceberg. They call them external tables. And we've actually already implemented this such that Snowflake, our Snowflake implementation, also uses Iceberg. BigQuery just released also the ability to read and write Iceberg. So what this has allowed us to do is we can tune our Iceberg indices. We can really make them work at scale. The engines, we can really like specify what we want because we know how features work. We know what materializations are going to do. We know how we can best achieve good results with Iceberg. So we can tune all these things once, and we know that each engine will be able to use our index to achieve good results. So what we've really done is we've, rather than before, where it's like we would have kind of the Spark S3 would be one plugin, and then Snowflake would be a plugin, and then whatever, Flink would be another plugin. Really, it's all Iceberg, and then you can plug in engines, and we support multiple different engines, including Spark, Snowflake, BigQuery, etc. So that was a huge unlock for us. The other unlock was with streaming. So one other value that we get from Iceberg and is that when you're writing data for a stream, we can also pipe that data into Iceberg. It will again be indexed in a way where we can run queries. So if we need to backfill for the last 2 months, we can do that very quickly and very efficiently. We even have ways with our PySpark scripts that allow us to unify both like a Kafka or Kinesis stream with the Iceberg table, so that you can write your query once, and we can process it on all the data that's coming in. Our incremental processing, which is not streaming, that would be like, for example, you want to run a job every 24 hours, but you only want to work on the new data. This is possible too, because Iceberg has snapshots. So with snapshots, every time you write to it, it creates a new snapshot. And in that way as well, I can keep track of what was the last snapshot I processed. And then I want all the new data since then. And I can get a delta. That's where the delta lake term comes from. I can get that delta and I can process that delta alone. And so if I combine those things, streaming, incremental processing, full batch processing, they all start to look a lot more similar. The trick, though, is that you really need to tune and understand all of the parts of Iceberg, and you also need to understand all of your processing engines, because a lot of this stuff is very new. Like with Snowflake, for example, it's like in the last, and BigQuery, it's in the last few months. Even in our work with Spark, we ran into bugs in Spark code because a lot of the Iceberg stuff, especially if you're really pushing it to the limit, you're just can enter territory that is less touched upon. So it's more likely that you will run into bugs and big issues. So what this has allowed for is as a data scientist, because I just talked pretty in depth about Iceberg and snapshots and all these things that Iceberg allows for. As a data scientist building features, one option is that you go and learn Iceberg, you go and learn Spark really in depth. How do you build streaming pipelines of Spark? How can I unify streaming and batch? All these things. Also, we have to be able to run jobs in Kubernetes to copy from things like Snowflake to Redis. We have Spark jobs that are really tuned that can copy from directly from Iceberg to Redis and Dynamo as well for materialization. So there's all this like data engineering work that Featureform has built in. It's like a harness. So one option is that you learn it yourself. Another option is that you get a data engineer who's very skilled to go and build this thing, which they'd be able to do. Like most good data engineers would be able to build a pipeline, perhaps similar to this. Or if you just use Featureform, all you need to do is give us the SQL query you want to run. And Featureform will go and put that in a state that it is the equivalent of a production grade data pipeline that a data engineer handcrafted. It's like at that same level. It's comparable to sometimes it's even faster, sometimes it's a bit slower. But the other nice thing about Featureform is that we actually allow for full tuning. Like any Spark flag you can set, any table flag you can set on Iceberg, etc. All those options are available to you. We have very good defaults, but if you really have a giant query and you want to tune it exactly, we're totally allow for that. So this really unlocked that promise of the virtual feature store. So building a feature platform where data scientists could define their features as code, providing versioning, lineage, all that stuff, monitoring on top. That was all doable. Like it was like more like building like a specialized data catalog. The orchestration was really hard because it's not really an orchestrator as much as it's like a compute engine, but it's a compute engine that we don't own. It's like a plug-in compute engine. And so we had run into issues in the past of scale. Like, how can we make this work at these really large data scales that some customers were coming to us with? And so the solution for us was Iceberg. Iceberg is what allowed us to be able to do this in a way where we weren't forcing the data scientist to go and build, or a data engineering team to go and build custom pipelines to make Featureform work. And so this is kind of the solution, the unlock of Featureform. Featureform is open source. This week, we will be releasing all of our Iceberg stuff I just talked about. All of those implementations will go into open source this week, which is why we're starting to talk about it. But check it out. It's on GitHub. Give us a star. And if you have any questions, I will be able to answer them now. But if something comes up later or you want to ask in private or whatever, you can always email me at simba@featureform.com. Or you can join our Featureform community Slack, where I'm very active and you can always reach out to me there. Okay, that was a lot of information. I'll pause for any questions that people might have. All right, we got one in. Can Featureform be used without a JVM, like using DuckDB and Iceberg? So without JVM, yes. Like you could argue, like we support ClickHouse, we support a lot of other products that aren't JVM focused. We don't support DuckDB today. However, there is potentially some work that's going to go into that very soon. There's an open source user who we're excited to collaborate with, who has offered to help out with our DuckDB integration. So yeah, more to come, but it's definitely doable. It's not like there's anything with Featureform that makes it not possible to do. It's just not supported today. And if you yourself need this for a specific use case, one thing that would help us is if you ping me, let me know, because it's just more data points I can use to allow me to put more time and people towards it. So that would also be useful. But good question. Any other questions I can answer for anyone? Awesome. Well, if anything comes up, you can always email me. Marie, maybe I'll hand off to you to do a little sign off of what happens now.
Yeah, sure. Thank you guys so much for attending this webinar. After this, I'll send you guys an email follow-up. It's gonna have the recording of this webinar. It'll also have links to our Slack community, so you can join that community. And if you have any questions about Featureform there, you can chat with the team, as well as other ML practitioners. And then I'll also send you any information about like our docs. Also, if you want to reach out to us and you have any feedback about the webinars, please give it to us. That's pretty much it. You're muted.
Yeah. Awesome. Thank you everyone who attended and yeah, hope to maybe hear from you.